last time. I'm pretty sure we finished up talking about array queues, right? We had the three ideas. We had the first idea where it was an array, and every time you enqueued something, we had to shuffle everything on down. And that's what the lab was this week. Then we had idea 2, where, well, you didn't shuffle everything down, you just kind of kept updating where the front was, but we had that issue of like, the queue kept like moving down in the array, and we had all that wasted space. So then idea 3 kind of addressed that issue by, whenever we got to the end of the array, if there was any open spots at the beginning, we would loop back around. We pretended the array was like a circle. That was idea 3. And that's the implementation I give you. And the trick to that was the whole mod right there, %, which gives you the remainder. And then we had an interesting expand capacity. We couldn't just, if we had a queue that looked like this, but the front was index 2, I couldn't just copy it over like I would have with the other array-based collections we had. Because now, like, well, the front is index 2, then the thing after the front is index 3, but then I have like indices 4, 5, 6, and 7 that are empty. But really, the thing at index 0 should be following the thing at index 3. We've got this gap in the middle of our data, and that's a big problem. So our expand capacity had to be a little bit more clever to do something like this, but then we even simplified it. I don't even know if I'd call it simplified, but we wrote it in such a way that it wouldn't copy it over like this. It would copy it over such that everything would be contiguous, but it would always reset the front to index 0. So that's how we implemented it. We didn't have to implement it this way, but we did. And this was just some implementation details we talked about, and yeah. So, the next topic is a more general collection called a bag. And a bag is it's more general than a stack. It's more general than a queue. And what I mean by that is we could do more with it. But the thing to note about a bag is the idea of what a bag is fairly high level. To the point that it becomes hard to answer questions about what we want to do with it with just the idea of a bag alone. You'll see what I mean. So a bag. Here's the idea of a bag. I drew it. That looks like a Ziploc bag. I don't know. It's just a bag that holds elements. It holds some data. By default, the data in the bag really doesn't have any ordering. For the high-level idea of a bag, there really is no ordering involved. If I say, what's the first element in the bag? Your answer is, well, there isn't one. It's a bag. There's no first. Put my hand in the bag and pull something out, but I'm not going to pull out the first one because it's just a bag. So the underlying implementation might be a linear collection, or a linear container like an array. But just because a thing exists at index 0 doesn't really mean it's the first thing in the bag. The idea of a bag is there's no real order there. But this is for the general bag. We're going to talk about specific ideas for bags in a moment. Like the other collections, we want ways to add things to the bag, remove things, check if it's empty, get the size, etc. But it becomes a little bit tricky. When I say, okay, add things to the bag, or remove things from the bag, it's not as well defined as a queue or a stack. With a stack, you add and remove things from the same side. Always. With a queue, you add things to one end, you remove things from the other end. Always. But a bag is more general. We might want to be able to add things in arbitrary spots, remove things from an arbitrary spot. So, how we add and remove things is a little unclear because it's not as obviously defined as it is for a stack or a queue. So, the idea of a bag is very high level. We can get a little bit more specific and start coming up with concrete ideas about how and why and where and what we do with them. And the first one we'll talk about is a sorted bag. And the next one will be an indexed bag. And an indexed bag is actually going to be very similar to your arrays or like a list in Python. But a sorted bag. If the elements must be sorted, then how they are added to and removed from a sorted bag is going to matter a lot. So if I have a sorted bag, that means all the elements in this collection must be ordered. But what's interesting here is the elements are ordered based on some property of the elements themselves, right? The bag doesn't determine the ordering. The elements themselves have some ordering with them. So if I gave you a collection of integers, for example, and I said add them to the sorted bag doesn't tell you how to sort the integers. Just the intrinsic ordering of integers tells you how they're ordered. If I say, does the number 7 come before or after the number 42, what do you say? Before. You didn't need to know anything about a sorted bag to know that. You just knew that because, well, that's how the order of integers is defined. So the orderedness of the elements in the sorted bag depends on what the elements are and how they are defined to be sorted. Interesting, too, is the elements that we add to a sorted bag must have an ordering defined for them. If I say add integers to the sorted bag, okay, yeah, you could do that. If I say add strings to the sorted bag, how would you do that?
Could you maybe run it through a hash code?
Hash code? Okay, I guess so.
Hash it maybe?
Yeah, hash it maybe. How else could you sort strings?
Use the numerical value for the letters.
Use numerical values for each of the letters. Okay, interesting. How else could you sort strings? Alphabetically, yeah, there you go. What else? By length? Sure. But the point here is, there's no obvious answer immediately, is there? How should I sort, if I had a collection of students, how should they be sorted? If I said you and you, how do we add them to the bag? Who comes first? Your answer is?
I don't know.
What are you thinking?
By grades.
By grades? How else could you sort students? Alphabetically by like last name or something. How else? Age, height, student ID. The point is, it's the elements themselves that would have to have the ordering defined for them. But if the elements don't have an order defined for them, we can't add them. We can't put them in a sorted bag because, like, well, it's not defined. What comes before or after one another just doesn't make sense if it doesn't have an ordering defined for it. We can define an ordering like we just talked about. Add strings based on their length. Great, there, we defined an ordering. But the elements themselves determine the ordering. Not us, not the bag. I mean, maybe we told the elements what their ordering is. But anyways. Yeah, so there we go. Strings, numbers in descending order, strings in alphabetical order. But the elements themselves determine the ordering. So if I said, add the number 58 to this sorted bag, there's only one correct spot to add this. If I said add, suddenly, like look, when I said the equivalent of add, excuse me, when I called the equivalent of add on a stack, push, we knew exactly where it went, the top. When I did the equivalent of add for a queue, in queue, we always know exactly where it goes. When we talked about a bag, and I said add an element to a bag, well, it kind of depends. Where do we want to put it? But if I told you that we have a sorted bag, and the whole thing of a sorted bag is that the elements are ordered based on the elements defined ordering, and I say add the number 58, there is now no mystery on where this should go. You know exactly where it goes. Unlike before, it wasn't like one end of the collection or not. No, it has to go in the one spot it would belong in this collection between 51 and 67. So now if I say, how do you add something to a collection that's a sorted bag, you now know how. At least the idea of how. You know where it would have to go. I can't put it anywhere else, because if I put it between the 40 and 51, that's not a sorted bag anymore. If I add it after 67, well, it's not a sorted bag anymore. It has to go where it goes. If we had a tie, if I said add the number 29, okay, fine, we now have a question to add. Do I add the 29 after the existing 29 or before? Whatever, doesn't matter. But there's one answer generally for where things are added. And then we can have an indexed bag. An indexed bag is going to be like lists in Python. We can add and remove things, but we can add things to the end. We can add things to specific indexes. We can reference the indexed bag by specific indices like we could in Python in the lists. This is the idea of an indexed bag. And it's kind of interesting to think about, but the indexed bag has an ordering as well. But the ordering is not defined based on the elements. The ordering is defined based on how I put the things in the indexed bag. When I say ordering, I don't mean sorted. I mean the thing at index 1 comes after the thing at index 0. There's an order there. Right? It's just the order isn't necessarily sorted. Does that make sense? Right? So sorted is an ordering, but any ordering is an ordering. So an index bag does have an order, but it's kind of more arbitrary. But the fact that something exists before another thing is meaningful in an indexed bag. Now, an interesting thing here too is when I add something, it's going to kind of mess up the indices of all the things. And then unless I'm adding something to the rear. Like for example, ignore the first two, ignore the light blue and dark blue. Only focus on the black box. If I added the black box to this index bag, okay, yeah, it's at index, it becomes the thing at index 7, right? And none of the other indices had to change. But if I add the blue box to the front, all the indices have to be, like, they get messed up, right? Because now the blue box is the thing at index 0, and then the one that was at index 0 is now index 1, and so on and so on and so on. So the ordering can be, like, altered, kind of, based on how we manipulate the data structure, but there's still an ordering, of course. Now, if I added all three things, I would have something that looks like this. Right? So far, so good? Now, these are just two bag implementations. I could add more. I have a sorted, I have a indexed. There's more I could add, whatever, it doesn't matter. I could come up with other implementation ideas, sure. But these are the two we're going to talk about. So elements can be added to any arbitrary index, assuming it's valid. So now the add, when I ask the question, like with the sorted bag, and I say, here, add this element, you know exactly how. It goes where it must go based on the ordering, the sorted property of those elements. With an index bag, if I say add this element, you will have to ask where. When we add, we have to know where we want to put it in that index bag. But that's fine, assuming it's a valid index. Now, if we have an index bag that looks like this, and I say add as index 74, okay, we've got a problem. That's index out of bounds. But we can just add any arbitrary index. So functionality. Here's an interesting idea that we're going to follow. I want us to note that first we talked about a bag. All right? But then we talked about two specific types of bags. We talked about a sorted bag and an index bag. They're both bags, though. So what I want to do is I want to define all the functionality. This is going to be an interface. I want to define the functionality that a bag should have. Then I want to define all the functionality a sorted bag should have. But there's going to be a lot of overlap here, isn't there? Because a sorted bag is a bag. Similarly with an indexed bag. The functionality I want my index bag to have, there's going to be some overlap. And there's going to be differences. But an indexed bag is still a bag. So this is where we get to an idea called inheritance, but more on this momentarily. First, let's talk about what we want a bag to do. We want to be able to add elements somehow. We want to remove elements, maybe a specific element. Check if an element is contained in a bag. So that would, like a linear search to see if it's there or not. Count the number of occurrences of a given element in a bag. So a bag can have duplicates. So I say, how many number 17s are in this bag? Gives me back 3. Well, there must be 3 17s in there somewhere. Check if it's empty, get the size, and then get an iterator for a bag. Now, we haven't talked about iterators yet, but iterators are this really handy tool of just being able to quickly and consistently loop over the contents of a collection. Realistically, if we were implementing all the collections we've done so far, your stacks, your queues, even the course list and everything, we would have implemented iterators, but we skipped that for the sake of simplicity. They're not overly complex, but we're going to be introducing them very shortly. They're really good. They're really awesome. We like them. And we do that by having this whole extends iterable thing. Now, extends is a new keyword, isn't it? We saw implements before. We never saw extends, though. Extends is the keyword when we are using like inheritance. But again, more on this momentarily. This is just saying that this interface is going to be implementing this right here, this iterator method. So our bag interface is going to include an add, remove, contains, count, is empty, size, or iterator. That's it for the bag. That's it. Any questions about this bag interface? It's really simple. It doesn't say anything about how things should be added. Notice that remove right there, that remove takes an element. When we remove from a stack, we didn't specify an element, we said pop. And that always meant give me the thing at the top of the stack. For queue, we dequeued. We always took the thing at the front of the queue, assuming it existed. With a bag, with this general bag, we say remove the specific element. And note that this remove doesn't return something of type T. The pop and the first and the front and the peak all return something of type T. This remove just returns a Boolean telling me if it was successful or not. So it's a little bit different. So I'm saying remove the specific element from this collection. If I have some collection of students, maybe you're all in there, and I say remove you because whatever, well, it would remove that one and return true or false, whether or not it was successful or not. So yeah, an interesting note there. Any question about any of these methods that we might want to have here? One thing I want to mention is if you think for a moment that this list of methods here for this interface is some divinely provided set of methods that must be there for all collections because this is super important, and what I'm saying right now, these are the methods you must have. No, I made this up. These are the methods I want my bag to have. If you're coming along and you're like, it really should have this other method, great, go ahead. This is just what I'm defining right here. This isn't set in stone anywhere. This wasn't handed down on stone tablets from the gods or anything. It was just someone somewhere. These are the conventions we typically include. Cool. Yes?
What's the difference between a bag and an object array?
A bag and an object array. Well, an array is still an array. And a bag will still only have elements of type T. An object array will be an array that can have anything of any subclass of object. So there's some similarity there, I suppose, but the array is still going to have a fixed size. Bags won't. In the same way that our stacks and our queues never had a fixed size, right? I mean, they did, but they didn't. If we had an array implementation, of course. A linked implementation is a little different. So it's good that you're thinking that, but that's kind of like more the overlap with like generics and objects. And when we use generics, it allows us to get a little bit more specific about the type of data that we're going to allow. And in fact, it's actually remarkable that you asked this question. It almost feels planted because of this. This is generic. But notice the type of the generic. Before we just said, okay, type T. But now a sorted bag. T extends comparable, and then another set generic, question mark super T. Who can tell me what that means? I didn't think so. More on that in a little bit. We'll talk about that when we get to the implementation of the sorted bag, but I'll give you a brief idea of what it means in a moment. Now, we want our sorted bag to be a bag. Everything a bag can do, a sorted bag can do. But a sorted bag has an add. Now, this really isn't that necessary, but this add, I really didn't need to include this because you'll notice here, Boolean add T element. Boolean add T element. It's already there. But the reason I'm including it here is it's a very special add because it's the orderedness really matters for the sorted bag. So that really shouldn't necessarily be there, but okay. And then we've got a remove first, a remove last, first and last. Now, I have all of these things as well because I have this extends bag T. That line of code at the top, there's a lot to unpack. Public interface sorted bag, and it's generic. Let's leave it at that for right now. Okay, ignore everything in the less than and greater than symbols right after sorted bag. So public interface sorted bag, generic stuff, extends bag. That extends means this is a bag. Everything a bag can do, a sorted bag can do. That is similar to me going up here and copying all this and pasting it in here. So even though I didn't explicitly write remove, remove exists for a sorted bag. If I went to implement a sorted bag and I didn't write the remove method, it wouldn't work. Because then I didn't implement a sorted bag. Because a sorted bag has a remove. Yeah?
Your laptop's battery's low.
What? Didn't I plug it in? Whoa, what's going on here? Oh no. Super weird. I don't think there's any outlet near me, is there? This is the closest I can get. Oh no. Let's see if I can move this.
James, you can just plug it into the desk in front of you.
Is there? Oh, good call. Yeah, good call. Hopefully that works and it's not a busted adapter. Holy moly. All right, looks good. The light's on. Good catch. Holy moly. You're on top of it, huh? All right. So there we go. And holy moly, look at that. Just in the nick of time. It's not giving me details on how bad it is, but it's bad. I'm glad you were paying attention. All right, so where were we? A sorted bag is a bag because we are extending the bag interface. Now, FYI, the next topic that we're going to hit is about inheritance. So don't get too worried right now. But a sorted bag is a bag. Now, what the hell is going on here? This is a way, I'm going to give a little bit more details on this in like the next topic when we actually implement the sorted bag, when we talk about the implementation of a sorted bag. But what that is exactly what I was referring to when talking right there about the object array. So the interesting thing with generics is we can put restrictions on the types that we allow for our generic collections. It's not just that the elements are, with a sorted bag, we can't get just any old type. No. The types we get must extend comparable. And that is just a fancy code way of saying they must have an ordering defined for them. Integers extend comparable. Ultimately. Same with floats. Anything with an ordering that you get by default in Java is extending comparable. If we wanted to write an object, if we wanted to create an object that we wanted to add to a sorted bag, we would have to define that ordering with this whole comparable thing. So all of this is to say, okay, we're going to have some objects of type T in this sorted bag, but those objects of type T must have an ordering defined for them. That's all that means. At no point, like if you ask me right now without looking, what's the code I write in there to enforce that it's like that? T extends comparable, question mark super T. I think I'm right. Yeah. But that's not something you need to like really memorize. That comes with practice. Long story short, it's the way to say the elements of type T must have an ordering defined for them. If not, you can't put them in a sorted bag. And the answer why should be kind of obvious, because, well, if the elements don't have an ordering, how do I put them into the sorted bag? I can't do that. There's no ordering. As soon as you ask who comes first, like which element comes first, I can't answer that. It's inadmissible. So the objects, the type must be, they must extend comparable, they must have some sort of ordering. Yeah, okay, not explicitly included in the sorted bag interface. The methods from bag are still part of what defines sorted bag. Sorted bag cannot be implemented without implementing all the methods from the bag interface. And the idea of inheritance is discussed more in the next topic. Index bag. An index bag, similar to sorted bag, it's going to extend a bag. An index bag is a bag. But what do we want to do? Well, we want to be able to add an element to a specific index, remove an element from a specific index, change or set the element at a given index to be whatever. So that would be like, okay, element at index 7, you should be 44 now. Get an element at a specific element, at a specific index, and find the index of a given element. Of course, with an index bag, this is all in addition to all of the methods that are there for a bag, because the index bag is going to extend bag. Note that the generic type for the index bag is just regular old T. There's no restriction. These elements do not need to have some orderedness defined for them. There's no sorted definition for them. There could be, but there doesn't have to be. An index bag is even more general. So we have add element. This right here, again, not really necessary because we would have had this one for free anyways because it came from the regular old bag. The add int And T, that's going to be add the specific element at a given index. Set, get, remove. Now note the remove here is a little different. The remove we saw before from the bag took an element of type T and returned a Boolean. This remove is different. It takes the specific index and returns the element at that index. So there is a difference. So there's two removes. Any question about these bags? Nothing? No, we're all good? All right. All right, inheritance. So inheritance is a way of deriving a class from some existing class, like we were doing here. This allows the ability to inherit from the base class. The base class being, in this particular example, would be bag, and the child class we'd often call it would be the sorted bag or the index bag. So here's an example vehicle, and then we can get more specific. We've got an aircraft or a bus. Obviously, there could be more subtypes. And then under aircraft, we can have different types of aircrafts. And under bus, we could have different types of bus, whatever. We could do this for a long time. More appropriately for Java, and what we're doing is, well, we have a bag. Now, mind you, an object is included at the top of this hierarchy because whether you like it or not, anything you implement inherits from object, even though we don't write extends object. It just does by default, it has to. Why? Because that's the way Java works. So when we made the bag, okay, bag inherits from object. That's why we have our equals and our hash code and our toString for free, but we often like to override them. We've got object, and then under that we have bag, and then we have the two subtypes, sorted bag and indexed bag. Sorted bags are objects, and they are bags. Then they're also sorted bags. But a sorted bag is not an indexed bag. Right? This is important. We do this hierarchical thinking in everyday life, of course. This is kind of like a generalization, with like abstraction in how we navigate the world. But I'm going to warn you. This whole idea of object-oriented programming, which is what we're doing here with Java, we make objects and the objects interact with each other to solve problems. When this came up, when object-oriented programming became like a thing, it kind of overpromised on what it was going to do. Without getting too into the thick of it, we have to be very careful as programmers not to take real-world hierarchical thinking and taking it as a one-to-one to our code. If you do, that becomes a recipe for disaster. One of the easiest, I'm going to jump ahead a moment. One of the easiest ways to avoid any issues with inheritance is avoid using inheritance. Avoid using inheritance on concrete classes. Inheritance is great for interfaces. When it comes to actual implementations of like implemented things, try to avoid using it. That's where issues come up. Anyways, some terminology. The class that is being inherited from is often referred to as the superclass, or the base class, or the parent class. I can guarantee you I'm going to use different variations of these words to mean that. Hopefully you can get a sense of what it is. The class that's doing the inheriting from the superclass is called the subclass, or the child class, or the derived class. But again, hopefully you can kind of get that relative relationship in your head. So the bag was the parent class, the superclass, the base class. The indexed bag and the sorted bag, those were the child classes. Okay, the derived class, the subclasses. Yeah. When considering the hierarchies, these terms are all relative, right? So, object, bag is the parent class of indexed bag, but it's the subclass of objects, and so it's all relative. Okay, object is always at the root of this hierarchy. There's an object class, not objects with an S. No, object, just object. Uppercase O, object. It's at the root of all class hierarchies. Every single class you've ever implemented inherited from the object class, whether you liked it or not. Yeah. It's done automatically. We don't extend object. Child classes inherit everything in the superclass. Everything. Every line of code written in the parent class we get for free in our subclasses. And when we think of the object class, yeah, in the object class includes an implementation of equals, toString, hash code. That's why if you start defining a class with no methods in it, not even a constructor, you'll have somehow magically an equals, a toString, a hash code already existing for that object that you're making, that new class that you're writing. You get those for free. That's because we inherited them from the object class. Again, often if we want to make use of these things, we override them. So we make the toString do what we need it to do. We make the hash code do what we need it to do. We make the equals do what we need it to do because we define it. But if we don't do that, we still get working implementations of all those methods. And what's cool about this is a way to enforce this whole inheritance thing. Kind of gives us a way to enforce that, look, if I have, think of generics for a moment. Just some arbitrary generic type T. I've got a stack of elements of type T. I've got a bag, sorted bag of elements of type T. Index bag of elements of type T. That's a better one. Sorted bag, they had to be comparable. So index bag, elements of type T. The elements of type T, they must be objects. Remember, we couldn't put primitive types for the generics. If we wanted the primitive types, we just had to use the object version of those things. So instead of int, we used integer. Remember? But because they're all objects, I don't care what the actual subtype is, because there is a guarantee that they all extend object. I know I can call equals and it's going to work. It's not going to crash, at least. All objects have an equals method written for them. So the generic, it's really happy to be like, oh, whatever type this is, I can call equals, because if they didn't implement it, it doesn't matter. I still have one for free, the one we inherited. It's pretty cool. It's a pretty powerful idea here. Yeah, we typically override, the equals, for example, is the same thing as the thisness, the sameness. Here is Java's collections hierarchy. If you open up the Java standard library, part of that standard library is the collections hierarchy, the collections. And there's a lot going on here, but you'll actually kind of notice two things. There's like a little bit of a legend in the top right. Interface, abstract class, class. Abstract class we haven't really talked about yet. You can kind of think of them as somewhere between an actual concrete class implementation and an interface. And we're not going to go into more details than that. But the point is, this is the hierarchy. And we actually only have concrete class implementations down here. Everything else is just interfaces and everything. So we have a tree set, a linked list, an array list, a vector, a stack, and a priority queue. These are concrete classes that you could load up for free in Java. Now, mind you, for assignment 3, you are not going to use that priority queue. You're writing your own. Assignment 4, you can use that priority queue. And each one shows what they're inheriting from. And you'll even notice in the collections hierarchy, there's actually iterable above it. That means that we've got that iterator thing, which is kind of cool. But we have iterable, and a subtype of that is collection. And the subtype of collection is going to be a set, a list, a queue. And then we also have this abstract collection thing, whatever that is. And then under set, we've got sorted set. And under that, we've got a navigable set, and so on and so on and so on. So this is the class. This is an actual class hierarchy in some Java code that you get for free in the standard library. Pretty neat. If you click this, I think it takes you to, yeah, where I found it. There's a Wikipedia page on the collections framework. All right, abstract class. Notice the abstract class designation. An abstract class is one that is declared with an abstract keyword. It declares, may or may not include abstract methods. An abstract method is like the signature, just like an interface, right? No actual implementation there, it's just the signature. It cannot be instantiated. You cannot make an instance of something that's an abstract class, but you can inherit from it. And that's kind of the idea. It's a way that you can kind of have, it may include some concrete methods and some interface stuff. So it's kind of like a cross between like a concrete class and an interface, where it can have some method signatures and some actual concrete implementations of certain methods. But you can't make an instance of one. You would have to extend the abstract class. If you're left scratching your head at that explanation, don't worry about it. It doesn't matter. We can move past it. Yeah, all right. The abstract queue has several important concrete methods implemented within the abstract class. Yeah, whatever. We can skip over this part. And where are we? All right, I'm going to stop here because polymorphism is a huge topic. But this is the general idea. We could have a stack reference variable, reference something of type array stack and link stack. They're both stacks though. That's the magic that we'll talk about tomorrow.